Hi everyone, I've scanned in the answer key to the extra practice problems for sections 4.1 to 4.5, and you guys should be working on problems 1 through 11. And you'll hear my voiceover explain each of the solutions that I've written here. Feel free to fast forward as needed to get to the discussion of the problem that you wish to hear being solved. In problems 1a to g, we're going to be finding the domain of the given functions. If you check out problem 1a, I see a square root. Therefore, I'm going to set what's under the square root greater than or equal to 0 and solve this linear inequality that I wrote down, isolating x to get x less than or equal to 10. So the final domain then is all real numbers from minus infinity to 10 inclusive. For part B, I'm going to set what's under the radical greater than or equal to 0 as well. But now, because this is a quadratic inequality, we are not going to solve it by isolating x squared. Remember that we've taught you guys to solve a quadratic inequality by factoring. And once you factor and find the zeros, which are -6 and 6, you must make a sign diagram. And in that sign diagram, you should be testing points in each interval on the number line. For example, testing -7. You will get a positive factor here, a negative factor here, which multiplies out to a negative. Testing 0 in here will get you a positive factor here, product multiplying out to a positive. And over here, if you test something like 7, you will get a negative factor here, a positive factor here, multiplying out to a negative number. Because we seek to have what's under the radical greater than or equal to 0, we are going to shade the positive, meaning the solution set, or the domain for this function, is the interval from -6 to 6. In part C, we'll also set what's under the radical greater than or equal to 0. Again, we have a quadratic inequality to solve, so we will factor it, getting the zeros to be -3 and 3. Again, doing a sign diagram, testing a point in the interval to the left of -3, the product will be positive. Testing something in here like 0, the product will be a negative times a positive to get a negative. And then testing something to the right of 3, like the number 4, will get you a positive times a positive, which is positive. Because what's under the radical must be greater than or equal to 0, we're shading the positives on this number line, giving the domain then in two chunks from -infinity to -3, union with 3 to infinity. In part D, we now see a function where, although we see a denominator, there is no variable x in that denominator. So you should recognize that this equation is just a linear function. It could be rewritten by breaking it apart as 1/5 x plus 1, and linear functions have no restrictions, so the domain is all real numbers. In part E, we see a variable x in the denominator. So we've been taught then that there's going to be a value or values of x that have to be excluded from this function's domain. We find those values by setting the denominator equal to 0 and using our algebra skills to solve the equation. In this case, I have factored. Setting each factor to 0 gives me x equals 4 and x equals -1. And then when I write the number line down for this one, there's no sign diagram needed, because all we're doing here is showing that we are just excluding the numbers -1 and 4 from the domain, because those would make a 0 in this denominator. So the domain then is reported in 3 chunks. Remember, these are open dots because this -1 and this -4 are excluded. So in 3 chunks, the interval is -infinity to -1, union with -1 to 4, union with 4 to 8. In part F, my eyes see an absolute value function. Again, I'm supposed to know that because I see no denominator, no x in a denominator, nor do I see a square root symbol, we have no restrictions. So we answer the domain as all real numbers. And in part G, I see a square root symbol. As well, I see a denominator. So in this function h of t, we must have what's under the radical be greater than 0, and The t minus 4 that's setting in the denominator then must be greater than 0, because 7 that's in the numerator is not going to affect this. This quotient, 7 divided by t minus 4, will be positive as long as t minus 4 is positive, which simply means that t must be greater than 4. Again, we did not write greater than or equal to, because if t was actually equal to 4, then that would put a 0 in this denominator, which would create an undefined quantity. So the domain of this function given in part g is the interval from 4 to infinity. On to question 2. We have this function f of x equals x squared minus 6x plus 8, with the instructions give the domain, the range, and the zeros. So this should be a familiar looking quadratic function. I'm going to create a graph here just to help myself answer this. Well, first I should know, because there's no square root and no x in a denominator, that this function is defined for all real numbers. So it doesn't take any algebra to answer that the domain is minus infinity to infinity. However, for the range, I need to know this parabola's vertex, so I went ahead and computed it with the normal x equals negative b over 2a. Got x equaling 3 there, plugged in to find the y value to be negative 1, plotted that point here. And to get the x-intercepts in the graph, I factored, set each factor to 0, and got the x-intercepts, as well the y-intercept and a reflection point. So here is a quick graph of a parabola. Once graphed, it should now be easy to see that the range of the function is all real numbers from minus 1 to infinity. And the zeros of the functions of this function are the x-intercepts that we solved for over here. Okay, now I've turned to page 2 of this problem set, and in my note packet it's page 72. On to problem 3. Well, in this case, we're talking about the function f of x, and we want to know that if we put a negative in front of the function, what kind of reflection this will create. Well, if you remember, a negative on the so-called outside of the function makes the y values on this function's graph become negative. And when the y values change from positive to negative, we get an x-axis reflection. Problem 4, now we put the negative on the inside. And when we put the negative on the inside, and we ask what reflection we're talking about here, this is going to make the x values change from positive to negative, and when that happens, it creates a y-axis reflection in the graph. Problem 5 gives two functions, f of x and g of x, and wants us to find f circle g of x. Well, remember, this f circle g definition is nothing more than the composite operation. We have to find f of g of x. Therefore, we need to plug g of x into this function f. So we go into f, and we replace the x with x plus 2, and we replace the other x with x plus 2, and we have then a minus 2. Simplifying, foiling out x plus 2 quantity squared, I get x squared plus 4x plus 4, plus this other x plus 2 minus 2. Combining the like terms gets me to x squared plus 5x plus 4. On to problem 6. Well, now I have a function f and a function g once again. And I'm going to be composing the functions, but this time it wants me to get g of f of x, so I'll be plugging the f into the g. So to plug f into g, all I take is this x squared and plug it in where I see the x over here. So if I get g of x squared, I get nothing more than the square root of x plus 2. Well, in order to find the domain of this function that I wrote down, what's under the radical must be greater than or equal to 0. Well, now this is a weird one. It doesn't factor. So if I think about this and isolate x squared, I get to x squared is greater than or equal to negative 2. But now, no matter what x I pick, squaring it is going to be something positive. So this statement, x squared is greater than or equal to negative 2, is true for all x. And since it's true for all x, the domain's all real numbers. Negative infinity to infinity for the composite function g of f of x. Okay, I've turned to page 3 of the extra practice set, page 73 of my note packet. On to problem 7. In this problem, we're given two graphs, f of x and g of x, and we're asked to find the following. To find the following information here, remember we're not plugging anything into equations, we're just reading graphs. Well, this graph of f of x is this right side up, thinner lined graph, and this graph of g of x is this upside down, thicker lined graph. So in part A, when I go to find f plus g of negative 3, I should be looking first for f of negative 3, and then adding to it g of negative 3. Well, when x equals negative 3, if I count 1, 2, 3 to the left, and I go get the y value off the f graph, I'm going to be right here on positive 2. When I go to get g of negative 3, counting 3 to the left and 1 down, I'm going to be having a y value of negative 1. 2 plus negative 1 equals 1. Part B. To find f of negative 2, I work on the inside first. So to get f of negative 2, I count 1, 2 to the left, and up 2. So f of negative 2 is positive 2. And now I insert that again. So to find f of 2, I go 1, 2 to the right, and up 2, and I have positive 2 for f of 2. Final answer. To get f over g of negative 1, I'm going to take f of negative 1 and divide it by g of negative 1. Likewise, I'm going to go to the graph to get these values. If I count 1 to the left, the value of f, after counting 1 to the left, is 1, while the value on g, after I count 1 to the left, is also 1. 1 divided by 1 simplifies to 1. To get f times g of 2, remember this little small dot is for multiplication. So I have to do f of 2 times g of 2. Likewise, reading the graph again, f of 2, counting 2 to the right, up 2, the y value is 2, multiplied by g of 2, 2 to the right, the value of g is 0 for the y value. 2 multiplied by 0 is 0. Part E, I now want the domain, range, and zeros of g. Assuming these graphs have closed dots on the end of g, I go to this upside down graph, and I'm trying to read g of x. Well, if I count from left to right, the domain would be the closed interval minus 4 to 4. And on g, if I count from bottom to top, the lowest and highest y value are minus 2 and 2 for the range of the function. And for the zeros, we know that means x-intercepts. So on g, again, this upside down, thicker lined V-shaped graph, there are 2 x-intercepts at 2 and negative 2. For part F, I now want to look at f minus g of x, and we're asking you in part F, where is this going to be 0? So now when I compare two functions, f minus g will equal 0 wherever the functions intersect, and that happens at two locations, x equals 1 and x equals negative 1. Where is f minus g of x greater than 0? That's wherever f is above g. So I'm looking on this graph up here, and I notice that f is above g over here, as well as here. So if I give those intervals where f is above g, we've got two answers to give, from minus 4 to minus 1, and from 1 to 4. And then finally part H, we want to know where f minus g is less than 0. F minus g will be less than 0 wherever f is below g. So in the interval from minus 1 to 1, you can see just by reading the graph that f is below g. I did not answer an interval notation in these parts because it's easier to answer these questions by just writing inequalities with the letter x, because we're answering for what values of x. So I'm satisfied here just using the inequalities with x. Okay, I've turned to page 4, now on to problem 8. So in problem 8, we're asked to graph parent functions. Going back into your note packet, you should be able to look these up. We've graphed them before. First, the parent rational function, f of x equals 1 over x. If you remember the table of points we created for this function, instead of just picking minus 2 to 2, we remember that 0 is where this function's undefined and is excluded from the domain. So we picked numbers near 0, negative 0.5 and positive 0.5. Once we find the y values, we then just plot our points and we end up with this rational function graph. Remember, when we give domain, it's all reals except 0. When we give range, it's also all reals except 0. In this rational function graph, HA stands for horizontal asymptote. The horizontal asymptote is the equation y equals 0. That's the way to give the equation of the x-axis. And for the vertical asymptote, we have x equals 0. In other words, the y-axis is an asymptote in the graph as well. In part B, the function here is called the cube root function. So in the cube root function, we have this table of points here, no restrictions in the domain, choosing nice numbers like -8, -1, 0, 1, and 8, so that we can give these cube roots of -2 to 2. Graphing the points, we get this shape, snake-like shape in the cube root graph, and the domain is -∞ to infinity. Likewise, the range is all real numbers -∞ to infinity. Now in problem 9, we want to graph the functions below, y equals -1 over x, and y equals the cube root of -x, by remembering what we know about reflections. What is the impact of placing a negative into the function's equation? Well, it depends on where we put the negative. So if we interpret this negative as being on the outside, in problem 9 right here, then the transformation rule is to take the x's and leave them alone while the y values are changing sign, because when a negative is on the outside, the y values change their signs. Well, that means we have an x-axis reflection. To carry out that x-axis reflection, it's quite simple to just take the table of points, leaving the x values alone and making the y values all negative. I'm sorry, not all negative. Change the signs from the y values that were above. When we make this graph, you'll notice that we have carried out an x-axis reflection. The chunk that was in quadrant 1 has flipped over the x-axis, and now it's in quadrant 3, while that chunk on the parent above that was in quadrant 4 has flipped above the x-axis into quadrant 2. When we go to the cube root graph, notice that the x has a negative on the inside, so that's going to make the x's in the transformation rule negative, leaving the y values the same. When we make the table of points, we therefore change the sign of the x's. So now I have +8, +1, 0, -1, -8, and we left the y values alone. And when we graph this shape, we can see that we have a y-axis reflection. What was in quadrant 1 right here flipped over the y-axis into quadrant 3, and what was in quadrant 4 right here has flipped over into the quadrant 4 on the transformation graph. So we have carried out a y-axis reflection. Okay, I have turned to page 5 in the problem set, and it's page 75 in my note packet. To work on problem 10, we have a piecewise function in 3 pieces. I've numbered them 1, 2, and 3, and I'm just recognizing that number 1 is asking for a piece of a line, while number 2 in the piecewise function is asking for a piece of a parabola, and number 3 a piece of a horizontal line. As per the instructions I gave you guys in class, I want you to create 3 tables of points. So for part 1 of the piecewise graph, the values of x we pick are -2 and less. The values of y are found from the equation y equals x plus 6. So I did some simple math to get 4, 3, 2, and 1 for the y values. The reason -2, 4 is circled right here is because this domain of x being less than -2 says I could pick any x up to but not including that -2, so we should be putting an open circle when we plot the point. In number 2, We're supposed to make a graph of y equals x squared from -2 to 2 for the x's. Here are the values of y squared, and then I plot the points over in the graph to the right, having all closed dots. So the dot right here got closed at -2, 4, even though it was open over here. And here's the other points. Okay. When I graphed section 1, I've got a piece of a line plotting the points for part 2 of the piecewise graph. I've got a piece of parabola. And for number 3, I've got a piece of a horizontal line. So I am carefully grabbing the points out of the table of points. When I got to piece number 3, y equals 4. Well, no matter what the x then is, bigger than 2, I plotted these points. And one thing again to notice, a little bit of a weird scenario. This should be an open dot because the x's needed to be greater than 2. But because the dot was already closed over here and closed right here, the 2 open dots that I may have had, that one and that one, both ended up being closed in this piecewise function graph. Well, now that the graph is done, we want to give the domain and the range. So when I go to give the domain, I realize that the graph from left to right spans the whole real number line. From the bottom, we go from -infinity up to a top of 4. There is no y value in the graph greater than 4. And I see 2 x-intercepts in this graph. If I count over here, it's to -6. And if I count it here, I'm right on the origin at x equals 0. Problem 11. If I have a graph with the point 5, 4 on some function f of x's graph, and I want to know what point must also be on the graph of the following functions, what I'm doing in this problem is testing your knowledge of reflections. So again, when I have a negative on an outside, negative right here on the outside, that's going to change the y value's sign. So I'll have 5, -4 must be a point on the graph. In part B, we've got the negative on the inside. That changes x's sign. So I have -5, +4 on the graph. And then if I change the transformation to x equals f of y right here in part C, that interchanges the x and y coordinates. So if 5, 4 is the point on the original graph, 4, 5 is on the y equals x transformation. And part D, we haven't spoken about enough yet in class, so please leave that out. As well, the remaining problems, number 12 to number 18, can be left out for now because we still have more to teach. I hope this helped.